Hey engineers, Timmy here. Let's solve the lead code problem of the day. Earlier in the day, I sent lead code 438, find all anagrams in a string, and let's just go through the solution. So the question says, given two string S and P, return an array of all indices of P's anagram in S. You may return the answer in any other. And for people who don't know, an anagram is a word or phrase formed by rearranging the letters of a different word or phrase using all the original letters at once. So for example, this is the word ABC, and an anagram of ABC would be ABC1, BAC2, CAB3, and I think there are possibly more, but you get the point. So, and yeah, let's just go through the solution, right? So, for this question, one of the things that we need to do is to be able to identify when we've counted an anagram in input S. And one popular way to do this is every time you see an input that is equals to the length of P, you sort it. You could always sort both of them to see if they give you the same amount of the same if they're the same string. But the problem with this approach is one, that is going to be time consuming because you would be sorting strings and you'll be possibly doing this in a loop. And so I won't, I opted out of doing that. And instead, what we're going to do is we're going to count all the unique characters of P, and we're also going to count all the unique characters of C that we've seen. And we check if the current character in S that we're considering is equals to the count of the current character in P, we're going to increment a variable that we're using to hold to see if we've gotten our matches. And if the length of the matches, that's the length of the characters that we've counted, is equals to the length of the unique characters of P, we would basically know that we found a match, and then we can update the output with the indices of the first character, right? So there's a lot going on in this question, honestly. So let me just go through the code, right? So yes, we'll be using counter. Counter is it's a popular it's a popular data structure available in Python, and so we use counter and we get and basically it just gives you a mapping of the count of every element in your input to the count. So for example, P, we would have a as the key and one as the value, right, and so on and so forth. So we also use the same for the frequency of S, but instead of using a dictionary here, we're using counter, right, because it is easy for us to detect if an element is in the counter object, or for us to not even handle cases where the element is not there but we want to increment it, right? And like I said, we use L. So this is a sliding window question. Yeah, so we use L as our left pointer matches to hold the number of variables, the number of matches that we've gotten, and the output. And I'm using enumerate here because I want the indices of each character and also the character itself. And like I said, we increment the count of the character that we're currently iterating over in S, and we check if C is in the frequency of P, and P's frequency, and the count of C in P's frequency and the count of C in S frequency is equal to the same. We increment and match. So this is where you are moving forward and you're also trying to keep track of if the character that you're considering is a possible anagram of P, right? But then what if you've moved forward, but then you one, how do you like you've exceeded the count of P? That's the first thing. And what if the current value that you're considering is an anagram? And so that's why we have to shift our window, right? Again, it's sliding window. This is not a video about explaining sliding windows. If you want me to explain that, just let me know. But yeah, so we shrink our window by checking if the distance between the left and the right pointer is already exceeding the length of P. and then what we do is we retrieve the current value, the current character that the left pointer points to, and we check if it is also in p frequency and the value is the same. It means that it means that fine, it may have contributed to a valid anagram before, but now we've added a new element, and so we have to shrink it, right? And so we reduce, and so it's no more a valid match, or we should not consider it in our matches. And so we basically decrement the matches, we decrement the count, and we increment our left pointer. So we move forward to shrink the window size. But if in the case where the frequency of that value is already 0, we delete it, and then finally we check if the match is equal to the length of the pre-frequency. So for example, in this case, when we've gotten to the index, right, to this index rather, when we've gotten to this index, we realize that okay, we have a matches of 3, and so it's equal to the same, and then we store the the index of L, and then we return our output. For the time and space complexity, it is it's O of n for time complexity. For space complexity, it's O of 26, because if it's read here from the constraints, S and P consist of only lowercase English letters. And so possibly because we're using a hash map and not a list, the maximum size of the frequency count would only be 26, which is equals to constant time. And algorithm is sliding window, and the data structure we used here is basically a hash map, but it's a counter, and underneath is a hash map, right, or a dictionary in Python. So I hope this explanation was really useful. I didn't know if you have any questions, just let me know. But yeah, that's it. Have a wonderful evening.